In this video, I'll be teaching you about the Diels Alder reaction. So in the Diels Alder reaction, there are two components. The first one is the diene. And if we take apart the word, di means two, and enes means alkene. And if you remember, alkenes are double bond. So diene means two double bonds. And as we can see here, we have 1, 2. In addition, something really important about the diene is that there must be a single bond in between. So in addition to the diene, there also needs to be a molecule called the dienophile, and that usually is any kind of double bond, as shown. So if we react these two molecules with heat, what ends up happening mechanistically is that this first double bond is going to attack this carbon here. This double bond is going to then move to this carbon. And finally, this double bond is going to move to the single bond. So, as you can kind of see, this forms a ring at the end. So we know that this is going to form a 6-membered ring. In addition, it's also very important to note that this double bonds move here. So there should be a double bond here. And if you're having trouble kind of seeing why this forms this hexagon, remember that you can always count your carbons. So if this is carbon 1, 2, 3, 4, we know that this here is 1, 2, 3, 4. And these last two carbons are carbons 5 and 6. So here is carbons 5 and 6. In addition, notice that this bond on carbons 1 to 2 moves to carbons 2 and 3, which is why we have this double bond over here. So something very important about the diene in the Diels Alder reaction is that it must be cis. And the reason for this is because if it is in the cis conformation, and remember cis means on the same side, then it is more reactive because of sterics. In other words, having the two double bonds closer to one another will have it be more reactive, thus leading to the formation of the Diels Alder product. So as you can see down here 3, try to identify which diene is cis and which one cannot be used in the Diels Alder reaction. So going over the answers, remember what I said about the diene. It must be separated by one single bond only. And if we can kind of see here, we have 1, 2 single bonds, and we also have 1, 2 single bonds here. So because of the single bond, because there are 2 single bonds, this cannot undergo Diels Alder. So now let's go on to the second problem. So as we can kind of see here, just from this conformation, this looks like it's trans because as you can see, they're not on the same side. But one thing you have to remember very carefully is that single bonds can undergo rotations if it's not in a ring. And this is because, if you remember, single bonds can rotate freely because it's not constrained like double and triple bonds. So because of that, if you try rotating the single bonds, which is usually annotated by this arrow, we can now draw in the cis conformation. And as we know, cis, the diene must be cis. So indeed, this does work. So now let's go on to the final answer. So if you can kind of see here, just from this conformation, this looks like it's in the trans position because as you can see, they're facing away from each other. So the question is, can this undergo rotation? And the answer to that is no, because as I said, only single bonds that are not in a ring can undergo rotations. Unfortunately, this is in a ring, and because of that, it cannot undergo rotation. So because of that, this cannot undergo the Diels Alder reaction. So now that we talked about the diene, let's talk about the dienophile. So as you know, while the diene must be in the cis conformation, the dienophile can either be in the cis or trans conformation. So as you can see here, this is cis because the R groups are on the same side, whereas the R groups here are in the trans positions because they're on the opposite side. So the conformation of the R groups are very important. And the reason why is when we draw the mechanism, so as you see, we know that this carbon is going to attack here, this double bond is going to attack here, and this electron is going to move here, thus forming a six-membered ring, like so. Now, because the R groups are in the cis conformation, they must be indicated on the same side. So you can get a product that looks like this, and remember, this is the wedge, so the R groups could either be both on a wedge, or they could both be on dashes, like so. And think about it in this way. Because it's cis, right, the R groups are on the same side, thus the resulting products, the R groups must also be in the same orientation. Either they're both wedges or they're both dashes. Conversely, for the trans product, after we draw the mechanism, right, we're going to get a six-membered ring like so. Because the R groups are on the opposite side, we must annotate the R groups as opposites. So one would be on the wedge, and one group would be on the dash. And to be honest, it doesn't really matter whether you have the wedge here and the dash down here, or have the dash up top and the wedge here, because remember that you can always flip the product and it's going to give you the same resulting molecule. So finally, I want to show you the Diels Alder reaction using the chair boat conformation. So in the previous problems, I showed you a resulting molecule that has a planar hexagon conformation. But now with this reaction, this is going to end up propping a 3D molecule. So what ends up happening is when you draw out the mechanism, this electron is going to move down here, this electron is going to move down to this carbon, and this double bond is going to move here. So visually, this might be a bit more complicated, but if we kind of label the carbons, right, if we label this as carbon 1, 2, 3, 4, 5, 6, right, and let's call this carbon star, right, what ends up happening is we're going to get a molecule that looks like this. Right? So if we transpose these number, this is carbon 1, 2, 3, 4, 5, 6, and this is the star carbon. So while we can see that this is a hexagon with some kind of carbon bridge here, right, this isn't exactly the best annotation of this. So we can basically transpose that image to look like a chair boat. And if you forget, here is kind of how you draw it. Right, so basically this molecule is the equivalent of that molecule. And don't forget your double bond. And if you need help labeling your carbons, this is carbon 1, 2, 3, 4, 5, 6, and this is carbon star. So as you can kind of see, carbons 1 and 4 are the ones that are attached to this bridge. Carbons 2 and 3 has this double bond, right, as shown, and carbons 5 and 6 are kind of like attached to just these carbons, right? And if you can kind of see just based on this mechanism, the reason for this is because this is a pentagon. And as we know, this carbon doesn't really involve anything with the mechanism. So because of that, that leads to the, chairboat top. So basically, in summary, anytime you see a carbon that's not participating in the mechanism, that's usually not going to occur in the ring. And because of that, that probably will lead to some kind of chairboat or some kind of 3D conformation.